Alright, hello everyone. This Python file, it contains a bunch of functions about prime numbers. Let's go through them. First, you have the SF function, which gives the smallest factor, right? So it will of course be a prime factor, and it's the smallest factor other than 1. If the number is prime, it just returns itself. So if n is divisible by 2, we will return 2 itself, and of course we won't be putting 0, right? So it's only for positive numbers, and also not for 1, because for 1 we would have to return 1, but that's not good. Okay. If I is equal, okay, so then we set I equal to 3, m is equal to the square root of n, and I should probably be doing the integer part of the square root of n only. Right, so that the comparisons are much easier now. So m is the integer part of the square root of n, right? While I less than square root of n, if n is divisible by I, will return I, otherwise will increment I by 2. So it's only going to check for all the odd numbers, and if this while loop it does not trigger this return statement ever, then we'll just return n at the end, right? Because that would mean that this is a prime number. So first of all, we're not dividing by any even number, right? So we have already divided by 2, right? And if it's an even number, we'll return 2 itself, and if it's not, we don't have to like divide by any other even number, because that's like redundant. We know that 2 does not divide it, so how can some other even number, right? Then what's this stuff going on with the square root of n? So if n is composite, right, then you can write it as a times b, where a is less than b. Then that means that a has to be necessarily less than or equal to square root of n, and b has to be bigger than or equal to square root of n, and these are of course integers, right? So we only have to check till square root of n, because in that way we'll figure out one of the divisors, right? We'll figure out what a is, yeah. And if we don't encounter any a which divides n, and that means n cannot be split as a times b, which means n is a prime number, right? This also works for squares. So n is equal to m square, then you can write it as m times m, and this thing is of course less than or equal to square root of n. This is bigger than or equal to square root of n. So we also have to check for the square root of n if it exists as integer, of course, and that's why integer part of this, that will include the square root of n if it as an integer as well. If it's not, then we don't have to check till that, so we can only check one less than that, right? So for example, like for checking n equal to 11, you just take like square root of 11, which is 3 point something. So we'll only check till 3. We won't check for 4, because that's more than 11, right? And a has to be less than or equal to, it can't be more. So since it can't be equal to, we'll just check for all the numbers less than square root of n. That's why integer part, right? Okay, and we are only checking for the odd numbers. So this is a fairly efficient way of checking if a number is prime or not. Then there's this other thing which returns the complete prime factorization of a function. So first we declare a list which contains x itself. So x is the input, right? We want to prime factorize x, and we say prime is equal to this list. Then while length of list is not equal to 0, that is whenever this list is not empty, what we'll do is we'll pop out a number from our list. We'll figure out what's the smallest factor of that number. If the smallest factor is equal to itself, then that means it's a prime number. So just do primes dot append s, and once we have popped out the element, that's no longer in the list, right? That's what pop out means. So yeah, so we'll just append it to the primes if it's a prime number, right? And now it's not in the list L, but it's in the primes list. Otherwise we will put that in, because now it's a composite, right? So we can split it even more. So L dot append s, but we also have to append the other factor. So if you appended a, right, you also have to append b. That makes sense. So L dot append integer of p upon s, right? And then we'll return primes once all of this is over. So this is running for like forever until the length of this list is equal to 0, right? So let's just run through an example. If your x is, let's say, 12, first iteration your L will be 12, right? So initially that's what's happening. L is this list containing 12. the primes list will call as capital P for now, that is empty. Alright, so is length of list equal to 0? It's not, so it will run this, right? Then what will happen is that it will pop out 12, right? It will see what's the smallest factor of 12, which is 2. It's not equal to 12, so it will put 2 in, and it will put 6 in. So now our capital L, that just becomes 2, 6. Our primes list is still empty, right? So that's the second. So actually this is the first time the loop has run, right? And first time running a loop, you get this thing. Then once again you run the loop, and now what happens is L is equal to, so it will pop out 6. It will make it 2 times 3, so it will yeah, what was I doing? Yeah, right. So 2 times 3, 6 is still composite, its smallest factor is 2, so 6 is not equal to 2, and that's why we'll append it again in the list. So it's just going to be 2, 2, 3, and the primes list is still empty, and then it will run again. So now it gets the first prime number, right? So it pops out 3 and it puts it in the primes list. So it's 2, 2, now there's no 3 in this anymore. And the primes list contains 3, and then after running the loop 2 more times, you'll get this thing, right? And there you go, you got the prime factorization of word number X, right? So yeah, that's awesome. Okay, so like what was I doing? Right, this function, this is not actually regarding prime numbers, so this just returns the maximum of, like, the maximum element in some certain list, right? So nothing to look there. Okay, then this is prime still, and this is actually a nice function. So like, there's an algorithm on the net which you can find on the Wikipedia. So this works like this. Suppose you have, like, let's just say numbers till 100, 1, 2, 3, 4, 5, 6, so on, and here you got like 11, 12, 13, 14, 15, 16, and just keep going like that, right? And you want to figure out only the prime numbers. So how do you do that? Well, first of all, what you do is you don't consider 1, right? Because if you start dividing by 1, that's going to be a nightmare. Everything is gone, right? Okay, so we'll start off at 2. So since nothing till now has divided 2, we know that 2 must be a prime, right? Everything less than 2, it cannot divide except 1, of course. We're not taking 1 into consideration. So 2 is a prime, right? And now once we figure out a prime number, we'll divide everything else in the list by this, and whatever is divisible, we'll cancel that out. So we don't want to be looking for this, for this, for this, for this, right? Next, you get 3. So 3 has not been divided by anything below it, which means it's a prime number. So 3 is a prime number. Awesome, right? And of course, if it has to be divided, it has to be divided by something less than it. So yeah, it is a prime. Then you divide by 3, and everything that's visible, you cancel it out. So like 9 will be cancelled out, and 6 will be, okay, that's already cancelled out, fine. 12 is cancelled out. Then 15 will be cancelled out, right? Then you go for 5, so this will cancel out 15 again, or cancel out 10 and 20 and so on. So in this way, you can get the list of prime numbers very easily. You don't even have to check if the number that we're getting is prime or not, because we know it will be, right? So I've made that into this code. So our primes list is once again empty at the start. Capital L is the list of range till n. So this is the list containing 0, 1, 2, 3, 4 till n minus 1. We're making L1 is equal to 0. So this element is L1, right? We're making that 0 because we don't want to be considering it. So whenever we get 0, we won't consider it, okay? So for I in L, if I is not equal to 0, primes dot append I, right? Yeah, k equal to I, while k less than n, lk is equal to 0, k is equal to I. Yeah, so we could probably make this more efficient by just considering whether or not we want that to be in the list. So making a list of booleans like true, false, stuff like that. So initially all will be true, then we'll make some stuff false, so on. right? But this is also good enough. So we're just containing all the numbers in our list, right? And whenever we don't want them to be considered, we'll make them 0. And if I is not equal to 0, we'll run this code. If I is equal to 0, we'll just skip over that, right? It will not divide everything by that number. Awesome. And yeah, so if I is not equal to 0, that means we have not divided that before anywhere, right? Because everything that's divided, that will turn out to be 0. So then you just have to append that, right, to our primes list. And then once all of this is done, you'll get all the prime numbers in our primes list. So then we just return primes. Easy. Yeah, probably not the best solution, because like we're gonna make this more efficient by considering a list of booleans and whatnot. But yeah, I mean, the whole idea would still be the same, right? Okay, then this is a function to return the sum of a list. Not important. This is going to print out the list in the console, which is actually not that useful, because for like million numbers you don't want to be printing this out. Then this is actually an important function. So this saves this list in a text file, okay? And you don't want to be looking at this code because there's no math involved in it, right? Okay, so now I'm just going to give you a demonstration of how it should be. So this is something that I ran before. So this is probably for like, I don't know what is the number. Oh, so this runs for quite a while. Okay, this is for 1, 2, 3, 4, 5, 6, 7. So 10 power 7. So everything that's in 10 power 7, right? All the prime symbols in 10 power 7. Those are in a text file now, and there are 6, 6, 4, 5, 7, 9 such numbers. Okay. Alright, cool. Yeah, what was I doing? So this is gonna take some time. We'll just start off with something that's easier to do. So okay, 2 million. That's gonna be good. Come on, what's your problem? Okay, just ignore it, because Pylance is sometimes like weird. I mean, it says something's wrong while really nothing's wrong. Whatever. We'll just run this, and just to be sure, I'm actually going to delete this saves.txt. So our saves.txt, I'll delete it. Yeah, move to trash. Okay. Are you serious? There's nothing wrong in this, really. Okay, and now I'm going to run this. Alright, it has run. And now we can see a new saves.txt. And now it contains all the primes till 2 million, right? So 2 million is the last one. I mean, 2 million is the limit. Okay. Look at that, 1999993. So that's the last prime number before 2 million. And this is the 148933th prime number. Cool. Isn't that awesome? Okay then. So this is what I wanted to show you. I'll see you guys in the next video. Alright, bye.